Good morning, everyone. I hope that for you, it is a beautiful day in the neighborhood. Let's see, who do I? Couple just questions here really quick. So Tiana, tell me really quick what your background is. When did you take Calc 1? And just want to get to know you a little bit. I'm not quizzing you.
I took Calc 1 last term with Mary Middleton.
Oh, got it. Okay, so you're at the other campus. Got it.
Yeah.
How about you, Elias?
I took Calc 1 last year with Annie.
Annie Giuliani.
And yeah, and then I took Physics 211, which had a little calculus this last term.
Mm-hmm.
So yeah.
Got it. That's awesome. That's all I was curious about. Let's see. I don't see Alyssa. Let's see any any issues with respect to. I checked quickly yesterday as to who was in class, and then also who got onto My Open Math. Any troubles with getting onto My Open Math? I don't see Becky, Julian, or Logan in My Open Math yet, or Cody. I don't know if I haven't checked to see if you're all here, but I don't know if this just happens to apply to you, but I left an old unimproved syllabus in Blackboard yesterday, which caused some people trouble getting in because it didn't have the right login and so forth. So the syllabus I sent you, and I fixed it over there, but it basically, I hope you're in My Open Math and up and rolling, but stay after class if you have any of those kind of issues, and I'll try to give you a hand making sense of that. But it looks like most folks are up and running, so that's good. By the way, welcome back, Thomas. Good to see you again. For those of you that are kind of new to my style, just FYI, I'm definitely teaching for what I call conceptual understanding, not procedural understanding. In the sense that, I certainly want you to be able to get your homework questions right, but I'm not just going to pull up your homework questions and then show you an example so that you can copy them. There's advantages if I do that because it sort of feels nicer. You can get your assignment done and so forth. But sometimes that's at the expense of, why am I even doing this and where? And so, as an example, yesterday I spent a lot of time with the concept of just what an area under a curve is if you just stack a bunch of equal width rectangles in there and so forth. So it's just important you understand that basic concept, and we're just gonna, we took 2 days with it, so we're taking another day just to kind of maybe do some more practical problems and so forth. But I want to give you one introductory thought with respect to kind of what the purpose of this is, or one of the things what it can do, like why. I mean, maybe you can appreciate that finding the area under a curve is, interesting, or somebody would want to do it. What is that area? Fine, but I want to give you kind of a application. So we spent a little time. What are you doing there? We spent a little time after class yesterday with some of the folks that stayed after. Just Becky asked a few questions like, what is this good for? Why would you ever want to find the area under a curve? It's neat you can find a curved area, but out in the real world, there's not a curve, and you never define the sides with a straight line and stop at the x-axis. Like, there might be weird areas out there like my lawn, but how does that apply to what we're talking about? And So we talked about that a little bit, but I want to give you one kind of, I don't know, maybe an illustration. One of the things that it gets used for actually, well, maybe something like in physics. So let's try this out. So I'm going to give you a velocity equation. So maybe you have had a little bit of physics, and I'm just kind of making this up, the square root of t plus 2. And so all you know is a velocity. And so fine. And so I can make a graph of that. I'm getting up my graphing calculator right now just to make a reasonable graph of it. I sort of know what the square root of x looks like, but might as well make it a little bit better. And well, actually, why not even go do it in Desmos? Let's do it right. So can't remember from last term if we decided it would accept this if I used weird letters. I'm assuming that you've played with Desmos a little bit, but it's so much more powerful than your graphing calculator that you're going to want to start if you haven't. Where did T go? There it is. Oh, it does work. Isn't that nice? All good, except for that was supposed to be a plus sign. So there's a velocity graph. And so you can see now looking at the graph, well, it started out at sort of time 0. It was going, we'll say 2 meters a second. Something's traveling 2 meters a second. But notice its speed is increasing. So by the time you get out to, let's zoom in a little bit. By the time you get to 1 second, now it's up to 3 meters a second. And by the time you get to 2 seconds, now it's kind of a decimal answer. But just looking at the graph, it looks to be a little bit under 3.5 meters a second. So this thing's speeding up. And so the point is all you have access to are the speeds. You know how fast you're going. And you can appreciate doing this in a car. This is accelerating. I'm going faster and faster and faster. I'm pushing the gas, going faster and faster and faster. And so great, I have this graph. So this is something you would kind of do in a physics class. So let's see. I'm going to take this graph after putting it in projector mode so it's large and glorious. I don't know if I remember how to do this. Seems like I could bring it in, but let me see if I can remember how to do that. Photo library, yeah, that was it. Beautiful. So let's stick that graph over here. So I want you, and I'll add this in here. So let's see if this down here on the bottom, this unit would be time. And we said that's measured in seconds. And up here on the y-axis, we said that's velocity. And that would be measured in meters per second. Why would I want to find the area under that curve? Or maybe I should ask, what would finding the area under that curve do? Your first thought should be, well, that's totally irrelevant. We're talking about velocity here. And so what does area have to do with velocity? But why would finding the area under this curve actually be pretty cool? Any brilliant guesses?
It would be the distance you traveled, I think. Yeah,
think about the units. I mean, area is height times, I'm gonna erase this, but I mean, if we're finding the area of a rectangle in here, isn't it height meters per second? I mean, isn't that what its height is measured in? Its units is meters per second. And then its width is measured in seconds. And since you multiply those meters per second times seconds, those seconds cancel out and you actually get your meters back again, which actually means the area under the curve allows you to find out how far you went. So if all you had access to is kind of a speedometer and you said, oh, look, I'm going 40, I'm going 50, I'm going 60. And over a period of time, you can actually undo that, almost work backwards, if you will. You could work backwards from, well, a rate of change. Remember last term, and we'll get into this in a couple of days, but remember last term, we were actually taking position type functions and taking their derivative to find the rate of change. And now this is actually going the reverse direction. You can take, if you're all you know is your rate of change, by finding the area under the curve, you can actually work backwards and figure out how far you actually went. So let's try that with this, just entirely with a graph. We won't even use the equation right now. But notice you have to say kind of when, like what are the limits? That's kind of the language we'll use here, the limits of this. So we'll say from t is, let's go, I don't know, 4 looks good. No, let's just go way up there. Let's go like to 6. Let's say from 0 to 6. And I guess what I want you to see is you also have to kind of decide what's your n going to be. Now, if it's 0 to 6, you could say, well, I'll suffer a little bit and let my n be 12. In other words, I'm going to do 12 rectangles inside that 6-second time slot. And, that'll be a little more accurate than if we just done 6, but far less accurate from yesterday if we did something like 100 rectangles. And then we also have to decide how are we going to define those. And so either left or right. So notice I'm going to come in here and draw out, and we're sort of lucky in this case because this marks out 1 and this marks out 3. And so actually those lines we have are our rectangles. So effectively it's going to be, since our width or our change of x can be found by taking our upper limit minus our lower limit divided by how many rectangles we have. So our rectangle width is 1/2 in this case. Again, you kind of don't need that formula when it's really simple like this, but you will need it if the number of rectangles is a lot larger. So I'm dividing it into rectangles. Do you see from yesterday that you have to decide then how are you going to decide how tall these rectangles are? And what you're going to see in your assignment is both. In other words, well, even 3. How tall am I going to call that first rectangle right here? Am I going to define it by its left side and therefore it's only 2 tall? Am I going to define it by its right side, in which case it looks to be like 2.7 tall? Or am I even going to define it by what's in the middle? That's kind of the question. And as far as your assignment goes, and you may notice this on the take-home quiz that I put in my open math, I'm asking for kind of all 3. Do it left, do it right, and do it middle. And if you only have one, you of course would kind of want to pick the middle. And so just because we didn't do it yesterday, let's actually do this as a kind of a middle. So you have right, left, or middle to choose from. So we'll say the height of our rectangles are going to be defined by the middle. And you can see that kind of makes some sense. So that's how tall that rectangle is going to be. This is how tall that rectangle is going to be. And this is how tall that rectangle is going to be. And notice there's, if you zoom in on it a little bit, there's middle is a great choice because we're basically missing this space. We're not counting that since our rectangle is too short to count it, but we are counting this over here. And so middle is going to balance that out. That's the area of that rectangle is going to be pretty darn close to the actual area under that curved section right there. So if you only have one, middle is a great choice. So let's see, am I going to draw all these in? Yeah, maybe I will. Let's go back to blue. Blue, why aren't you drawing for me, blue? And this is sort of a pain because 12 rectangles is quite a few rectangles. If I'm just doing this by hand, that's about the most I ever want to have to do. But I want to give you a second to kind of evaluate what you think this area is. Now, would you understand that in this case, because I actually gave you the equation, you don't have to guess at what that height is? But would you agree you can kind of guess at the height? Some of the questions in your assignment will just ask you to estimate the area under that curve. And so couldn't I just look at that first one and say, well, that middle to me looks like it hits, since this is 3, it looks like it hits about 2.5. So then that first rectangle is 1/2 wide by 2.5 inches tall, or 2.5 meters tall, I guess I should say. And so I can just estimate this. I don't have an equation. You'll have problems where they just give you the graph and they don't tell you the equation at all. And so you're just guessing. You could even be given this in a table. In other words, what if you were just told that from 0 to 1/2 a second, you were just told what the speed was? They traveled a speed of 2.5, and that was just listed in a table. So there's all kinds of ways you can kind of be given this. But the main thing I want you to see here is just that area under a curve actually takes what was a rate, meters per second, since you're multiplying meters per second for the height times seconds to cancel, you end up with meters. Like the answer to this is going to be a distance. It's going to be how far you traveled in those 6 seconds, when all you actually had access to was the data about your speed, which is kind of cool. And it's one of the sort of physics applications for this. So I'm going to introduce a little bit of notation today. We need a sum, which in math is abbreviated with this Greek letter. Anybody know what that Greek letter is called? Should be the first time you've ever seen this, unless.
Is it called sigma?
Yeah, it's called sigma. How'd you know that, Jaleesa? That was you, right?
Yeah, I was in chemistry, so.
Got it. Showed up in chemistry. Cool. Yeah, it gets reused, and maybe this is putting you on the spot, but what was it in chemistry for? Was it adding things up? That's what its symbol means here, but.
For one of our first assignments, we had to learn the Greek alphabet.
Oh, got it. Yeah, because a lot of those things come up. You have a good memory then.
Thank you.
We use that in electronics too, for like capacitors and resistors and stuff like that. When you sum it.
Yeah. So it's not a fancy symbol, but it's the kind of thing if you show somebody, and again, this is part of the secret code that, you're joining this elite club that knows calculus. And so if you show somebody this symbol, they're going to think you're doing some crazy stuff. But again, most of life, if you actually look into it, is not as complicated as you think. This is just a symbol that means add stuff up. Mathematicians are lazy. They don't like to write words out. Don't want to write out the word add or write out the word sum. And so let's just use S for sigma as a symbol that means add up the stuff. And so this is not very difficult. When stuff is difficult, fine, let's let it be difficult. But if it's not difficult, let's not make it difficult. So would you agree that since from yesterday, all of the widths are 1/2, instead of multiplying each one of them by 1/2 out of laziness, I could just save the multiplying by 1/2 for later, factor it out. And so now I'm going to use the equation, and I'm just going to kind of cheat in my graphing calculator as I did yesterday to do this. I'm going to make a table really quick, starting at 0. And so again, we have to decide, are we doing right, left, or middle? Well, notice because we decided middle, this gets a little more complicated, because what am I typing in? What am I typing in to get this height right here? I need that height, the middle height. So what is it I'm typing in right there for my X? It's not 0 or 1/2. What is it?
Isn't it a fourth?
Yeah, it's a quarter. So that'd be a quarter. And then what are you doing to get to the next one and the next one and the next one? And this is going to be important. as we look for ways to try to speed this up and not have to add thousands of rectangles and so forth. Now
You're
that
just
I've been
printing by a half.
Yeah, you're adding that width. You're adding a half. So this is a fourth plus a half, or 3/4. 3/4 plus a half, which would be 5/4. So I'm putting in a fourth and 3/4 and 5/4 and then 7/4. And so middle is like, you got to think a little bit more, right? So in my table, I'm going to go back to table set, and I'm going to say I want you to start at 1/4, and then I'm going to increase the table by half. And now I can say, show me the table. And the table is just telling me all of these heights that I've got to add. And so notice the picture would indicate that the middle of that is around 2.5. And when I simply plug in one-fourth into this equation up here, that's exactly what I'm getting. Square root of 1/4 is a half, and 2 plus a half is 2.5. And so I'm getting, I'm gonna switch colors. I'm getting 2.5 here, and I'm just gonna write you a note, if you look at this later, that that's V of 1/4. So that's my first height. The next height I'm getting is 2.866. And that, of course, is V evaluated at 3/4. And that's the last one of those I'm going to write. Now I'm just going to write down the list of the things that I see in my calculator. So that saved me a bunch of time. And I've got 12 numbers. And so again, this is kind of pushing it. And notice in this case, I am taking a square root. And you might remember square roots give you decimals that go on forever. And so what I'm suspecting that what I'm looking at in my calculator right here is rounded off, 3.3. I'm going to choose to round everything to 3 places, no matter what it tells me. So that's 3.23. And the next one comes out exactly 3.5. I don't know why. I mean, I got to look back and see. Maybe I landed right on something that's a perfect square. Maybe it was 9/4. The square root of 9/4 is a perfect square. Probably that's what I landed on, maybe. So I got 3.5 and I got 3.658. Again, what I'm looking for here is you to have a conceptual understanding of what we're doing. So I'm purposely, I don't know, taking a little bit of time and writing stuff out just so that you have time to think for a second. And as I said before, I'm very interested that you just interrupt and ask questions on the fly. 3.937.
Well, I've got a question. What's the point of the epsilon symbol here if we're just kind of writing out all the pluses and stuff anyway?
Yeah, good question. So later on, what we're going to try to do tomorrow is write a formula for this. And it's already indicated a little bit by what I wrote in orange here. In other words, instead of writing every single one of these numbers out, what I'd like to do is write a formula instead of writing all the plus signs. So you're onto something.
When you have a minute, can you show me the table in the calculator? Yeah,
absolutely. Let me write these out and I'll do it. See, 1, 2, 3, 4, 5, 6, 7, 8, 9. I made it to 9 numbers. 4.179. There's 10. 4.291. There's 11. And my last one is at 5.75. Let's see, does that make sense? The X value is 5.75. Yeah, that would be a fourth short of 6. And so 5.75 makes sense. And I'm getting 4.398. So those are all my heights. Does that make sense to you? These are all of my heights. I've got my width. I only had to write it in there once instead of writing it into there every single time. So if I just add all those up, say times a half, I have a darn good estimate. Do you agree with that? A darn good estimate. Since I chose the middle as my choice. Let's see. I guess I don't have a choice but to quickly add those up. But again, doesn't this feel like something that would be nice if a calculator or a computer program was doing it for us? And I'm actually going to show you how to write a computer program in your graphing calculator tomorrow that will iteratively do this. Because I think that's kind of cool to know, even if you're not a computer person. And I would definitely not describe myself as a computer person, but because this calculator is written in BASIC, it's actually pretty easy to do this, even without computer knowledge. And so it's kind of good for you to see, I think. All right, I'm almost done. 4.179. Of course, do you also agree that I'm running a big risk, and also because I'm, hurrying, because I'm sort of wasting time writing all this down, of typing one number in wrong. All I get is type one number in wrong, and then I get this thing wrong. And so I got 43 point, and I think I'll write this out just in case one of you checks me and fixes it because I did it wrong. That's what I got for my sum, 43 point, and then of course I'm multiplying it by a half, and I got an area of, I'm going to say approximately because I'm going to round it off, 21.8. And the important thing in this problem is you're not done unless you actually write out, meters. I mean, the whole point of this is, wow, that's amazing. You actually just, all you knew are these speeds, and your speeds were actually changing. They were going faster and faster and faster each time. And you're able to take the speeds, and by using the area under a curve, you were able to reproduce how actually far you went. So in that first 6 seconds, again, in case I did something dumb, you traveled around 22 meters. So that's kind of cool that you can actually work backwards to figure that out. It's one of the physics applications for this, and one of the reasons it was invented. So let's take a quick look at just what I had sitting in the calculator to kind of pull that off, just because you are going to be asked both in your assignment and in the quiz that I gave to do this sometimes when there's a lot, like 40 rectangles. I remember that in your quiz, 40 rectangles. I've got to cheat to get all these answers. I can't just plug everything in. So here is what I typed. So I'm going to the y equals screen, hitting clear, typing the square root, second square root. I can't have t, so I've got to have x. It made me start with a parenthesis, so I got to put that in there. And then I said +2. So now I kind of have my graph if I want it. Same graph, but notice way uglier than Desmos. So now I'm going to go into table set. There's table and table set, second table set. And I wanted to start, because my first one was at 0.25. I wanted to start at 0.25. And then I wanted to increase, enter, clear. I wanted to increase each time by 0.5, my width. And mine says auto and auto, so I can say cool. And then I can say, to get to table, I can say second table. And there's all of the heights, automatic. Now, again, do you need to do that? No, you can use the trace command. You can say, I'm over here in graph, and I can just say trace. After it's graphed, I can say trace. And anytime I want to type in, like one of my answers was 0.75, I can type in 0.75, and it takes me to the graph and says, there's your y coordinate, 2.866. You don't have to do it this way. It's just kind of neat to see that there's technology to do this for you. And I hinted a little bit that Excel will do this too. And Excel's kind of even better because I not only can have them all written out, but I can ask Desmos or I can ask Excel to add them all up for me. Again, in my case, I'm fairly doubtful that I even got the answer right, because I had to type all 12 of those numbers into my calculator correctly, and probably I didn't. Again, it's early, but interrupt immediately. How's that? Does that make sense? Are you able to pull that off? It is kind of a cool shortcut. So by way of, in a sense, introduction, that is, again, one of the purposes of finding the area under a curve. So it's kind of, it's funny because it's not actually an area. You're not getting an area here. Really, what you're actually getting is meters.
Hey, Doug, I have a question.
Please.
So I know tomorrow we want to build our formula using stigma, but I have no idea how stigma works. Like you say, it shows that you're supposed to build the sum, but like I've seen stigma used in certain textbooks and it has stuff above it and stuff below it, and I don't know how that incorporates into making a formula.
Yeah, I think we should say that right now. Since I introduced it, let's introduce that a little bit. Well, in this case, didn't we work our way? It was important to us. Let me just highlight some things that were important to us. It was actually important to us that we said we're going from 0 to 6. Does that make sense? That's our limits. We're saying I care about the time from 0 to 6 seconds, but in the real world, you have all kinds of times you might choose to care about. It could be 0 to 12 seconds, or even 5 seconds to 9 seconds. So that's what goes above sigma. Now in our case, so I don't know if I'm going to do this completely, but sigma. Does it make sense in our case that we had 12 things to add up? So if I say from 1 to 12, then I'm saying add these 12 things up now. And let's see, what did I add up? I added up 1/2. And then what did I multiply by? Or what did I, what was the height? Well, the height was, let's see, what I plugged into this square root of t plus 2 equation. But what did I plug into the square root of t plus 2? Well, first thing I plugged in was a fourth, right? I plugged in 1/4 into the square root of that plus 2. The square root of that plus 2. Wasn't that my first answer? I mean, this right here was my 2.5, if you will. That was my 2.5. But how am I going to get the next one? So this is saying add them up. And this is also what Felix's question was, is, what's the purpose of the dumb sigma symbol if you're going to write all the plus signs there anyway? How do I get the next one? Well, that's kind of where this k equals 1 to 12 is sort of a symbol that says first k is 1, and then k is 2, and then k is 3, and so on and so forth. So when k is 1, great. Well, notice there's no k in this. Okay, well, let's see. Maybe I'll stick a k in here. Well, how do I get that? Would you agree that back here, to get to that 3/4 right there, I had 1/4 plus sort of 1/2. Isn't that what I did to get 3/4? I added a half to it. But how do I get to that 5/4? Isn't that also 1/4? Except for it's actually plus 2/2, isn't it? See logic in that? So in a sense, that's my k right there. So what this is like, these, if you will, are kind of my x's, right? I mean, that's how I'm getting my x. I still haven't plugged them in yet, but that's what I'm doing to get x. So actually then I've got to kind of modify this formula down here a little bit and say, no, it's really not. Let's see, do I want to erase it? It's really more complicated than this. I guess I don't have any choice but to erase it. It's really more complicated than that. I've got to say this is actually 1/4 plus k times a half. So when k is 1, wait a second, that's not working. Does it work when k is 1? Do I get the first answer?
No, because you put your half on the outside, didn't you?
Well, also the plus 2.
Yeah, and I still have the plus 2. Again, all I'm really working on right now is just to get the x's. Well, let's see. First of all, do you understand if I put k as 1 in there, because this says start at 1, does it make sense I have 1/4 plus a half? That's 3/4. So my first x is 3/4, not a fourth. How could I fix that? Well, here's a way I could fix it. I could go back and say, how about if we went from k is 0 to 11? Isn't that still 12 numbers? Now if k is 0, then my first answer is 1/4, right? However, that was just x. What did I do to get y? I had to plug that in. And what did I do to that? Well, I took the square root of it. Didn't I have to plug that in, which said take the square root of it and then add 2? That sigma statement right there is identical to this giant list of numbers. If you stick in k is 1 and then k is 2, I'm sorry, we start at 0. If you stick in k is 0 and then k is 1 and then k is 2 and then k is 3 all the way up to 11, you get all of those green numbers. Now with only 12 of these, I would say that sigma notation is more trouble than it's worth. But what if there were 100 of them? So that's kind of the value of sigma, and also the part of this that starts to feel a little bit painful. So anyway, we're going to tackle that tomorrow. While we're on sigma, let me just give you kind of a simple question as to what today's questions are going to look like in your assignment. There's no application to them, but if I just asked you separately, brand new problem, and I said, let's go from k equals 2 to 7. And again, what that represents is, oh, from 2 to 7, let's see, that's 5 or is that 6? Rectangles that you need to add up. And now what are you doing to those k's? Well, let's do something kind of simple to them. Let's just say, let's take k and let's square it and add 3k to it. So what you need to see is, hey, that's just a symbol that says add up a whole bunch of stuff. But the stuff you're adding up has got a pattern to it. Didn't these green numbers that we have back here had a pattern to them? We added a half each time and we plugged them into the equation and got an answer out. So these green numbers that we added, there was kind of a pattern to them. And this equation right here effectively represents a pattern that you might be able to write down. And so all you have to do is say, oh, sigma is just key for sum. See, that's just a code that means sum. And I start out with k is 2. Oh, that's easy. I put 2 in there. 2 squared is 4. 3 times 2 is 6. 4 plus 6 is 10. So my first answer is 10. And then I move to k is not 2, but k is 3. And I plug it into that equation again. And the sigma is the reason there's a plus sign here. Sigma means sum. 3 squared is 9. 3 times 3 is 9. So my second term is 18. Now I move to k is 4. 4 squared is 16. 3 times 4 is 12. 16 and 12, I think, is 28. So then I move to 5. 5 squared is 25. 5 times 3 is 15. That's 40. 6 squared is 36. 36 and 18, 54. And lastly, k is 7. 7 squared is 49. 49 and 21 is 70. And then I just add all those up and there's my answer. That's all sigma notation means. It's a cool way to write down adding up lots of stuff. And what I hinted at yesterday is these estimates are not going to be that good unless we have a lot of them. Does that make sense? We can't just have 12. If we want a really good answer to something, we can't have 12. Well, we've ultimately got to have infinitely many of them. We've got to have infinitely many rectangles. And so this sigma notation will help us to get an answer. And again, this should feel a little terrifying, except for just like in Calc 1, taking a derivative seemed kind of painful, but in the end, we had all these really neat shortcuts, and the same thing's going to happen in this class. So we're going to leave sigma in the dust the end of this week, start of next week, and we'll sort of never see it again. So all I got to do is add all those up, and I'm done. I think I'll add that to the notes later, but I don't want to waste your time to do it right now. So that's all sigma means, and I think I gave you some sense of why that's being introduced here. How's your brain? Is it overloading? Is it hurting? Anything you want to ask about that?
So is it basically gonna kind of go away like it did with the definitions of the derivatives in the first class? Like it's like, hey, this is the long way to do this.
Yep.
And then here's how we do this the short way.
Yep. So what makes calculus amazing is there is a shortcut. Thanks to computers, we could just write routines. And again, I'll show you in your, as I said, in your graphing calculator, how to write a routine that will do this automatically for you. And we'll be able to type in the variables. In this problem, the variables were, what's the limits that you're interested in? We said 0 to 6. So I could say 1 to 7, whatever limits I wanted. And then, what's the equation that you're talking about? We had an equation there that we were finding the area under the curve. And then how many rectangles do you want? That's the other variable. Do you want 8 rectangles? Do you want 16? Do you want 50? But computers will add these up for us without having to write all this sigma notation out. But it will take a little bit of an understanding about kind of what we did right here. That statement right there. To get to each value, we basically added a half every time. Every time we got to our value, we added a half to our x value, and then we plugged it in, right? And so we'll make a routine in our calculator that will do that automatically. And as I said yesterday, if there was such a thing as a computer, when the idea of finding the area under a curve occurred as an interesting thing to do, maybe as a part of a physics problem, probably calculus, the shortcut, wouldn't have been discovered, if you will. But yes, I find the sigma thing to be, you'll find that to be a little bit painful. It's not going to feel very good. So you'll be glad to leave that in the dust, to be my guess. For today, let's see if we can, I'm going to try to give you some time to think about this on your own. But again, let me just give you a random, kind of a random graph. So all we're doing right now is estimating the area. We can never get it exactly right unless there's infinitely many rectangles. And so all we can do is estimate. So let's estimate the area under, and I'm going to give you just a kind of a weird equation, and you're going to need your calculator to kind of pull this off. Let's see, let's make that plus, we did the last one +2, let's make this one +1. And let's do that from, and I'll say this the way the assignment says it, from x equals 1 to x equals 4, which is kind of a waste of time. Lazy persons would say, just say from 1 to 4. That means the same thing, right? That's interval notation. So that has to be decided. Unless you give boundaries to the area that you want to find, then it makes no sense to go after the area. What decisions do we still have to make about this since we're estimating?
How many rectangles do you want?
How many rectangles do we want? And let's make our life a little sane by saying 6. 12 seemed too many. N equals 6 rectangles. And as I said yesterday, even though we have better ways of estimating using trapezoids or something of that nature, because we're working our way to infinity, we can just keep it simple and use the formula for a rectangle. So N equals 6 rectangles. Is that all the decisions? Are we done?
Left, right, or middle?
Yeah, the other one is left, right, or middle. Now, if your goal was just to estimate it, maybe now you see, based on the graph that I just showed you a second ago, that you should choose middle. But you need to be able to do all of them, at least as far as your assignment. And it's kind of good to see that they all give slightly different answers as you look at the graph. And so let's see if we can do, well, all of them. So let's first do left. And I want to give you a second to just, like, that's all you get. Can you graph that? On your graphing calculator, only for the purpose of stealing the answers that you need to steal. We're going to get lost in shortcuts this term. And so my largest concern here is that you look at this and say, all I'm doing is adding up a bunch of rectangles. Like that's all this class is. We're going to have awesome shortcuts and so forth. The last term, it was just find the slope of a curve. Do we have all these fancy ways to pull it off? Yeah. As far as the picture is concerned, did you survive the fact that the width is always found by going, let's see, how far, what's my range? Well, I'm going 4 to 1. So 4 minus 1, that's 3. I'm dividing by 6. So I got half. My width is a half. Hey, that's the same thing we had a second ago. My width is a half. And so now I know where to draw these rectangles. So I'm going from 1 to 4, a half at a time. And notice my particular graph doesn't show me where a half is very well. And I showed you yesterday that program that I found / edited in Desmos that does this automatically. And that's awful nice. It draws it perfectly, but you should be able to do it yourself because this is not complicated. So far, if you know a formula for the area of a rectangle, you can be in calculus. But what does it mean that it's left hand end pointed? So I can see down here my 6 rectangles, and because it's left hand end pointed, then these are the areas that I'm interested in. So what I now realize is that I'm going to get an underestimate. Since I'm missing all of these areas. They're all missing. We're going to proceed to the middle. We'll do the right next. And then the middle, I want to do them all. But I just, all I want to do is like have the right answers and then you confirm that you got that. You might even go into table set and see if you can get that all to work. And compare what you're getting to the graph. I chose for no good reason to round off to the 100th place when I wrote these down. I mean, it's an estimate, a terrible estimate anyway, right? However, in your online homework, you got to be a little careful with this. Because if they say round to 2 places, your final answer to 2 places, then you better not be rounding these to 2 places along the way. Do you understand that? You better at least be going to 3 or 4 places, or maybe even storing them in your calculator. But you could get this wrong if your final answer is supposed to be to 2 places and you round your numbers along the way to 2 places. Hope that makes sense to you. Again, I'm not supremely confident. I didn't make a math mistake, but I got 8.0565 for mine. Again, on a test or something, I'm not going to say anything about rounding, and I'm not going to care about rounding. And if you write everything out like this and you just have one number written down wrong because you did something stupid and your work is clear like mine is, then I'm probably not going to take off any points for this.
Yeah, I accidentally added, I included the y value for x equals 4, so my answer was a little higher. It was
Nice job. And notice that's kind of why the picture is important. I really am thankful that you mentioned that, Cheyenne. It's really easy to accidentally include the last, like put 4 in there. So one of the things you want to check that I just checked a second ago is, do I actually have 6 numbers down here? Because I have 6 rectangles and those are all their heights. So I should only have 6 numbers, not 7. There's all kinds of little things that you could do that don't represent a misunderstanding, but you will get the answer wrong as a result of it. So have you moved on to the right? And I want you to see all these in the same problem, just so that you kind of understand what they have in common and also the comparison value. So I think it helps a lot to have a graph to look at, for me personally, because it just makes it simple. It makes me realize, oh, this isn't complicated. But you should notice that you're still working your way from 1 to 4. So you should have, and your width is still a half. So you have all the same lines you had originally. It's not complicated. But this time you're defining your height as the right side, which means your area is these rectangles all added together. Almost the same picture, but this time, now I see that I'm including all of these these triangles. Again, they're not really triangles. These are kind of added in, I guess. I don't know how else to say it. But the point is that's going to make this an overestimate. Not only do I know it's an estimate, but I even know it's high. Last time I knew it was low. So already I'm expecting, since the last one was 8.06, I'm expecting, I don't know, 8.5, 9.2. If I don't get that, then maybe that's how I catch, like Cheyenne's mistake. She probably had 9 or something, maybe you catch that mistake. So I'm expecting something more than 8. I don't know how much more. Maybe it'll only be 8.3. But if it's 20, I'm thinking that doesn't make sense. But what I'm interested in here is how is this different than the last list? I mean, I'm still doing the same thing, right? I'm saying, okay, let's go find the area. And I'm telling myself that that's approximately, my width is a half. But what do these lists have in common? Well, now they're defined by kind of these points, kind of the right side points. Well, hey, I already had that list. In other words, the 2.31, which was the height of my second rectangle in the previous problem, is the height of my first rectangle. And so it's the same exact list. Did you notice that before? Probably you did not. I don't think I would have. So all I need then is kind of, well, the one for 4, which is 3.52. And because I had typed all of those in my calculator, then I don't have to retype them all again. I can go back in there and say, give me that list back again. Give me that list back again that I had before. And I'm just going to go in and take the 2 out of it. I'm going to go replace the 2 with the 3.52. And if I do that, I get 17.65, which when I multiply by a half gives me 8.825. So I didn't know how much more to expect, but definitely more. Does it make sense that just averaging those two and calling it 8.4 would actually be a pretty reasonable guess now? If you were just estimating it and nobody told you to choose the left or choose the right, if I did both of these and averaged them, 8.4 is probably a pretty decent answer.
I don't know why, but the left just feels so much more natural than middle or right.
Yeah, well said. I feel exactly the same way, because don't you find yourself wanting to start at 1? Since we're starting at 1, don't you find yourself wanting to plug 1 in? So I think you're right to think that. And again, what's kind of cool about this long term is you're going to be able to do this starting at 1, because we're going to let there be infinitely many rectangles. And if there's more rectangles, can you appreciate if there's more rectangles? Let me erase this, but this one would have probably came out like 8.3, and this one would have came out like 8.5. They're just going to squeeze in toward the answer because there's less waste. That's what we saw yesterday. And so when we let there be infinitely many rectangles, they're going to be the same exact answer. They're going to squeeze to the same thing, and it won't matter whether you do left, right, or middle. So we won't care. And so you're right, Connor. We'll probably just stick with the left side. And finally, at the risk of beating this horse to death, let's even do the middle. I'll draw the picture, but I'll probably just, I don't know, we'll see what I'll do. Interestingly, I don't know if the middle is going to be an over or an underestimate. I don't know if you know what I mean by that, but remember, those are not triangles. Go ahead. Say again?
Would that mean that if you did the middle, or so would that mean the middle is exact?
The middle is not exact. It would be exact if those were straight triangles that we're messing with on the top, but they're curved. And so the question is, when a little bit is left out and a little bit is added, which one is it? So this is not working because it's curved. I don't know if that conceptually makes sense to you, but.
No, it makes sense. My internet connection is terrible, so it's like everything keeps kind of skipping.
Yeah, sometimes when you're blocking them here and
following for the bar.
As before, you're still making all of your heights a half apart, starting at 1 all the way to 4. Nothing has changed. It's just that this time you're defining your height as, well, the middle between those two. So I'm going to mark out all those middles so I don't screw it up. There's my middles. So those are all my heights. So of course the problem is then I've got to figure out, what are those locations down there? I got to think a little harder. Let's see. I started at 1 and I went half of a half. So isn't that 1 1/4? That's 5/4, I think. And then I add a half to that, which is 2/4. So this would be 7/4. And this would be another half, another 2/4 added. That'd be 9/4. I think I'm on it now. Again, do you see the sigma notation thing? I started at 5/4 and I'm adding 1 2/4 and then 2 2/4 and then 3 2/4 and then 4 2/4 to it. So now I'm up to 11/4, 13/4, and finally 15/4. Those are my X values. So again, if you didn't see this before, the middle's a lot more trouble. But again, let's zoom in on this a little bit, just so you're understanding the complexity. That's getting added when it shouldn't be, right? Because it's not under the curve. This is missing. So this is getting added when it shouldn't be, whereas that's actually missing. But can you see visually that they kind of balance each other out? Can you also see that they're not the same? That's why this isn't perfect. Doesn't the one on the right look a little bigger? Now, it could look a little bigger because my drawing is bad, which is actually true. Would you also agree that that red curve right there, because we're zoomed in so close, is almost straight? And so they actually should look pretty darn equal, but they're not because of the curve. I don't know if that you agree with that.
Is there ever a case where doing it from the middle is actually worse than one of the sides? Is there any way for us to know that?
That's a great question. And I think that would have to do with if the curve was real undulating and crazy. Because we're choosing really mellow curves that have really kind of definable behavior. So yeah, that's a great question. And the reality is you got to use some common sense. And also in the real world, if you had some reason to estimate this, there's a time to underestimate and a time to overestimate, right? Like you're in the store and you're thinking, I'm buying a bunch of stuff. Do I have enough money? I mean, you want to kind of overestimate the prices of all the stuff you're buying just to make sure you have enough money. So you might round everything up. How much is this? $3.89. We'll call it $4 then. Round everything up to make sure you actually have the money that you need. So now I got to plug 5/4, 7/4, 9/4, 11/4, 13/4. So toward sigma notation tomorrow, isn't this 5/4 plus, let's see, 1, 2, 3, plus 3 of our widths? Isn't that how I got there? But in my case, I'm just going to go to the graphing calculator. There's only 6 of them. This isn't that hard to write down. So I'm going to go back to table set and I'm going to say, let's start at 5/4 and then give me the table. And so my table says, of course, it says in the decimal version, but it says 1.25 and then 1.75 and then 2.25. So it looks like it's working. So then I'm getting an area of, and don't forget the 1/2. 1/2 times all of those added together. Again, I'm rounding off. So I'm getting 2.16 plus 2.45 plus 2.72 plus 2.96. And again, my calculator list is just listing tons of these. So I got to make sure to stop at 6. I got 4 numbers there. 3.19 is my 5th. And finally, my 6th is 3.41. Again, before I even type this in, what am I expecting? Well, I'm expecting something between 8.8 and 8.0. So I'm expecting about 8.4. And so if I don't get that, then something somewhere is wrong. So far, I think I've been lucky because none of you have said anything about making a mistake or you got something different. But this time I got to retype the entire list. One question I'll ask you is, do you think this answer is the exact average of the previous answers? Could I just average those previous ones and I'll get the same answer? I'll let you think about that. I got 8.445. Again, this is kind of embarrassing. This is brainless. Like we're adding rectangles. Like this isn't calculus. I mean, again, I'm going really slow here because I want you to have a super firm conceptual understanding of all we're really doing in this class. We're trying to answer this question. We just need more rectangles.
I checked to see if what you said was true, and it is. The average of the left and right is the middle.
So it is correct. Maybe you can all think about why that might be. Now I'm about to show you something that I should not show you because that is my nature. I'm always showing you the shortcuts too soon. You want to know what the right answer is? Watch this. Whoa, easy, partner. X raised to the 2. Oh, this calculator is a little different. X raised to the 2/3 plus 1. There's my graph. Remember last term in my class anyway, the cheat button I showed you that'll find the slope for you automatically, like cheat and just say, hey, what's the slope when X is 2? Remember where that was? That was behind calculate. Second, calculate. Right there, dy dx. That was calc 1, right? Well, there's calc 2 right below it.
Should we be seeing your screen right now?
That's a good question. Yes, you should. User error. So there's the graph. Excuse me a second, I just unplugged my computer's power cord. There's the graph. So last term, the cheat button was behind calculate right here, second calculate. And dy dx right there was the cheat for finding the slope, right? So we cheated last term and said 6. So it's basically sitting here saying, okay, great, you want to know the slope? Well, duh, where? Because the slope is different every place you go. So I say, I want to go to x is 2, and I say enter, and it says, there's your slope, 0.529. Perhaps you remember if I put you to it. Could you do that yourself? Could you take the derivative of x to the 2/3 plus 1 and then plug in x is 2 and get the same answer? You may remember, oh, x to the 2/3, that's power rule. That's easy. I actually remember that one. You don't need the cheat button to get that, but that's kind of cool that that's sitting there. What do you notice that's right below that though? And I want you to stare at that statement for a second. That's what we've been doing. What have we been doing? We've been adding rectangles. What does dx and f of x represent about a rectangle? What's dx?
Is it the width?
Is it, I like the way you said that. Is it the width? You're not sure. Yeah, it's that width down there. That's the 1/2 a second ago. That's the little, notice it's got to be tiny for this to work, right? So the fact that it says dx implies not just that it's the width, but it's a teeny width. Frankly, infinitely small width. And what's f of x?
The height.
The height. And so didn't we multiply those to get the area of a rectangle? But then what did we do with all those areas?
We added them up.
We added them up. There's another symbol that I'll be introducing in a couple of days. There's another symbol right there that means add them all up. And so that's a pretty cool statement. So I'm going to say 7. What does it ask me? It asks me a question that it should be asking me, which is, well, where do you want to know the area? I can't tell you what the area under that curve is unless you tell me where you want to be. Well, we wanted to be lower limit 1, enter. Now it asks me, not surprisingly, for what's your upper limit? Well, for us, that was 4. Is it going to ask me how many rectangles? What do you think?
No.
It's not, because dx means infinitely small rectangles, infinitely many rectangles. So this is infinitely many rectangles, which is why it just tells me the answer right now. And beautifully, it even shows me a picture of it. There's the right answer. Accurate to, what is that? 6 decimal places. Again, I shouldn't be showing you that this early. But it's kind of cool to check your work, I guess. And it will be cool for us to check our work later on. But isn't it cool that that's, well, a program that somebody wrote inside there that is adding billions of rectangles. And I'm going to show you how to write that program yourself tomorrow. It's only about 6 lines. It's really simple, actually, just because it's kind of neat to know how to do. And so do you agree that that point there, that kind of shows that our midpoint estimate was the best one, but it
To the
isn't the same?
point.
What'd you say, Connor?
I said to the 100th point, I was pretty surprised.
Exactly. Darn accurate. And that's basically because our curve was so, to Felix's point, so kind of mellow. But, you know, if it went real crazy, then the midpoint could be off. That's why it's kind of neat to have a picture of it and so forth. But as we leave 5.1, like, is this complicated? Finding the area under a curve? This is not complicated. You can teach this to anybody. It's not calculus yet. The shortcut is what makes it calculus. The concept here, super simple, just like last term. Find the slope of a curve. 252, find the area under a curve. Not complicated.
I have a question on what numbers are in the table set because my decimals are like a little bit off, so I'm not sure if I have the wrong number in there.
That's interesting. So let's find that out. So first of all, did you have this typed? It's really easy to type this wrong. Like in this calculator that you're seeing right now, you are seeing this still, aren't you? Did I say
Not
stop
anymore.
share? I think I said stop share. Yeah, in this calculator right now, you have to have those parentheses for 2/3. Otherwise, it's only raising x to the second. So for instance, you could say x squared divided by 3, and it's not x to the 2/3. And so there's some, you could have typed something wrong there. You might, is that it? Yeah, parentheses. Some calculators kind of put the 2/3 up in the exponent so you can tell it's working. Okay, let me show you one more thing. And I'm showing you this because we have a few minutes in because it's in your assignment. Anytime I have what I consider to be extra time, that's kind of what I'm going to do with it, is do what I can to help you be prepped for your assignment. But to me, what we just did is a spectacular example of the simplicity of what this is supposed to do. And so again, yeah, we saw that our answer was actually only off by 2 thousandths. That's awesome. And that was rounding my previous numbers up here. I rounded these numbers off like more places than I could have. And so maybe that could have even been better had I not been a little lazy. As I mentioned a while ago, though, you know, could you do all of this from a table? So let me give you a table. We'll say this is minutes, and we'll go with 0.369 minutes. And anybody know what that abbreviation is?
Is it gallons per minute?
Gallons per minute. So in a sense, we'll say this is like, you know, water leaking out of a tank, or maybe a pump pumping water into a tank or something like that. But gallons per minute is a common measurement for the speed at which liquid, because liquid is gallons. That's a common designation in the real world for kind of how a pump, if you bought a pump online, it would say something like how many gallons per minute it can pump. If you're going to be a fireman, that would be something you would study deeply, because your ability to put water on a fire. Notice it's going higher, 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 but you know, what if it kind of lowers a little bit at the end? And so all you knew, if you're sort of standing there operating the pump, is you set it to 80, and then 3 minutes later you're like, this is taking forever. And so you set it to 86, and then you set it to 94, and then you're like, oh, okay, it's too fast, I'll back it off to 88. But can you see that the question of, you know, how many gallons are actually pumped now, when all I have access to is the rate? So could you, from a table, like a second ago, we had to plug our X's, in a sense, these are our X's. I had to plug those into an equation to get my F of X's or my Y's out, right? I had to plug it into an equation. Well, here, you're just given to them. This is actually easier. But I could see if you saw this in an assignment that you would think, I don't know what you're asking me to do here. So of course the question is really, you know, how many gallons? And I might say in this case, since the table went from 0 to 9 minutes, I'll say how many gallons from, you know, kind of at 9 minutes, assuming that we, had it turned on from 0 to 9 minutes based on that. But you got the same problems we just had in the previous section. In other words, how do you want this estimate to work? Do you want it to be a left-hand endpoint estimate or a right-hand endpoint estimate or a midpoint estimate? I want to just give you a second to think about that yourself rather than me just immediately launching into it. And what's the width of each rectangle? This is different now. You don't have a formula. Can you draw a graph of that? Can you picture a graph of that without drawing it? Can you tell how many rectangles are sitting here just from what I gave you in the data? Zero, 3, 6, 9. I don't know about you, but I was honestly, when I said how many rectangles, I was thinking 4 when I said that. But now that I drew the picture, what's the answer? Well, remember, you don't have an equation here, so you don't have any more data you can go get. So you have no choice. You have 3 rectangles because you can't know what it was at 1 minute. You can't say, I'm going to have 12 rectangles because you don't know the answers to those. You have nothing but a table. You only checked your watch. You only looked down in this situation. So you have 3 rectangles here. And the height of the first one is given. In other words, this one is at 0. When you first turned it on, it was at 80. And then at 3, it was up to 86 and then up to 94. And then actually back down to 88. So in a sense, if I was to connect that with a smooth curve, but it's nothing different. It's no different.
So instead of trying to like estimate the middle, would you just take the average of the left and the right?
Yeah, or you could just give an upper and a lower. I think the question in your assignment, just to help you out a little bit, is actually not saying left and right. It's actually saying give us an upper and a lower estimate for this. And what's a little bit interesting about this, let's see, I'm just looking at the chat, which I try to do occasionally. Please interrupt too regarding those things because sometimes I won't see them, but you guys can be more than welcome to talk to each other in chat. If you say something in chat and I don't comment on it or don't happen to see it and somebody else comments and asks a question, again, you're going to learn so much more in this class if this is a conversation and not a monologue, me just rambling along. So Logan said, couldn't we have 4 rectangles with 4 heights since 4 heights are given? The answer is kind of. I'm going to erase this, but I'm thinking out loud because I'm actually not sure what your answer is, but you're sort of thinking about something like this, right? Like those are the heights. Is that kind of what you're thinking? I don't know. Would that work? It bothers me that part of that one is over there and then I'm not sure. Actually, I don't know. That's a good question. I haven't thought about that. But one safe thing you could do, I guess, is just to kind of do the left hand. Let's see, is this right? And notice, interestingly, that last one is kind of off the page, if you will, but we're defining it by its left side, right? And so notice my my change of x here is 3. So I'm basically saying if I did this from the left-hand side, I'm saying my area would be 3 times, well, my height was 80 and 86 and 94. let's see. Or should I include, is it 4 rectangles? Is it only 3?
Yeah, because that
If-
includes time past what we
Exactly.
know.
So see, this last one isn't there, and that's kind of what I was getting at. That last one's not there because we're only from 0 to 9. Does that make sense? Because what I just drew is taking it clear up to 12.
If we did right, would that mean we would only be able to use 3 rectangles, where if we did midpoint, it would be 3, but if we did the left side, it would be 4?
Yeah, isn't that weird? Like you, let's draw both of them just to kind of make sense of it. But if you're staying between 0 and 9, then your rectangles have to live between 0 and 9. And so this is definitely what left would look like. We'll go back and draw right in just a second. So, but it's kind of funny how this it isn't as clear as it first appears. It appears like, oh, this will be easy. But it's maybe it bothers you that 88 is entirely left out of this. So if I add those up and multiply by 3, I'm getting an area that's approximately 780. And interestingly, again, what's the unit? You missed the whole point if you don't put the unit here. What's the unit?
Gallons?
Gallons?
Yeah, because you're multiplying heights of gallons per minute times widths that are in minutes. Gallons per minute times minutes, then your unit is actually gallons. And so what's cool about this is you're saying, oh, well, how much water did I pump in those first 9 minutes? Well, a low estimate would be 780 gallons. But what if we did right? Let's switch colors. I gotta shut up here, see the time. What if I did the right? Well, now my area for that first one would be defined by that point. The second one would be defined by this point. And the third would be defined by that point. So I'd actually have 3 times 86 plus 94 plus now 88 gets included. Notice that last one actually went down. And so this one, because it goes up and goes back down, it is not just that the right answer is the average between these two. It's not that simple. When stuff goes up and goes down, that kind of screws up whether you have an over and underestimate. And this has got both. And so I don't even know what kind of an answer this is going to give me. 86 plus 94 plus 88 is 268 times 3 is 804. So because I paid attention in this one to the first 3 numbers, and this one I paid attention to the last 3 numbers. This represents kind of an upper and a lower estimate. So if I was to guess, I'd say somewhere between like 790 or something like that, 792, whatever. It's just an estimate. And notice this, a long time has passed. Your change of X here is gigantic. 3 minutes is a long time. And so this is kind of a terrible estimate because it's only 3. But again, it's kind of cool that you actually don't need an equation to model this. You just need data. You can collect data and pull the same thing off. And if all you need is an estimate, then great. If you needed a better estimate, then you better check your gallons per minute more than every 3 minutes. You better check it every 1 minute or something like that. But it's just kind of cool that you can do that. Okay. If you have a second, I'm gonna show you one more thing here. But just to make sure you're kind of getting the benefit of this. So from yesterday, let's see, I've shared a screen. I'm going to my open math. You are seeing this, right? No, I don't think you are. You're not seeing this. Now you are. So you should be going in here every day, you know, if you need to. Maybe you don't need to. You only go in here if that's your assignment. But as I said, after class every day, I'm going to go in here and go into class notes. So there's 5.1 notes from 111. So there's everything I wrote yesterday. And there's the video lecture. I have to kind of download that and it has to process. And so it isn't available right away. But if you missed a class, part of class, or just want to re-go over it because you realize after you get into the assignment that I don't really understand this as well as I thought. I think I'll go watch a chunk of that again. I'm going to put that in there as quickly after class as I can. I don't have a class right after this. I have one at 11. So I usually kind of work on that immediately. But those will be in there every day. So take advantage of that whenever you need to. All right. Stay after and ask questions.